Hello and welcome everybody to another episode of Books and Bytes. Okay, let's unpack this. We're diving into some truly mind-bending ideas today, drawn from David Deutsch's book, The Fabric of Reality.
It's definitely a deep one. We're looking at how things like quantum computers, time travel, maybe even the universe's ultimate fate might all connect through advances in physics and computer science.
Yeah, and our mission here is really to guide you through Deutsch's arguments for this, unified view of reality. We want to pull out the key insights from the material.
Right. At its core, the book weaves together four main strands. You've got quantum physics, specifically the many universes idea, then the theory of computation, focusing on the Turing principle,
Okay.
epistemology, that's the theory of knowledge, heavily influenced by Karl Popper, and finally the theory of evolution, thinking along lines like Richard Dawkins.
And the key thing Deutsch says is these aren't separate subjects. They're like fundamentally interwoven, necessary parts of the whole picture.
Exactly. Not just pillars standing side by side, but threads making up a single fabric.
That integrated view is fascinating.
Yeah.
And he kicks things off by challenging something most of us probably take for granted, the very purpose of science itself.
Yeah.
We usually think it's all about prediction, right? Figuring out what's going to happen.
That's the common view, yeah. But Deutsch argues pretty strongly that the main point of science isn't prediction, it's explanation.
Explanation.
Yeah. Prediction is crucial, obviously, but it's more like a tool we use to test the explanations. It's not the ultimate goal.
He uses that great analogy, the spaceship one. You wouldn't say a spaceship's purpose is just burning fuel, even though it has to burn fuel to work.
Right. Burning fuel is necessary, but the purpose is carrying the payload, getting something somewhere.
So experimental tests are like the fuel burning, necessary, but the real payload of a theory, its actual purpose, is to explain the world.
Precisely. And what makes an explanation really deep? Often it involves talking about things we can't directly see or touch. Atoms, distant galaxies, the laws of nature themselves.
These that are kind of abstract.
Exactly. The further removed these explanatory concepts are from just raw experience, the deeper the explanation usually is. And Deutsch insists these things aren't just like convenient stories, they're part of the actual fabric of reality.
So real understanding isn't just piling up more facts, it's about building these deeper explanatory theories. You contrast like an ancient master builder with a modern engineer.
Yeah, that's a good way to put it. The master builder had loads of specific rules of thumb, maybe some guesswork, knowledge passed down.
They could build amazing things, sure, but that knowledge was often quite narrow, right? Tied to specific materials, specific places, hard to innovate.
Right. Whereas a modern engineer uses fewer theories, but they're much more general, much deeper, based on understanding fundamental principles like physics or material science.
And those theories apply much more broadly. You don't need totally new rules to build something on the moon or with some new alloy.
Exactly. You use the same deep theory, plug in the facts about the new situation or material, and the theory tells you how it should behave. That generality is key.
You see that even in specialized fields like medicine, don't you? This sort of unifying trend.
Definitely. As we understand the underlying, say, molecular or genetic reasons for diseases, conditions that look totally separate start to seem connected.
So a doctor who understands those deeper mechanisms might be able to figure out how to approach a really rare disease they've never even seen before.
Because they grasp the principle, the underlying explanation. And this drive for deeper explanation, this is what leads us to one of the really big, maybe controversial ideas in the book, the multiverse.
Ah, yes. The many universes idea.
It's absolutely central to Deutsch's whole picture. And he argues the key evidence isn't some weird astronomical thing. It's right there in basic quantum physics. Single particle interference.
You mean like the double slit experiment, where even one particle, like an electron, seems to go through both slits and interfere with itself somehow?
Precisely that. Deutsch says, if you are genuinely trying to explain that phenomenon, it unequivocally rules out the idea that only our universe exists.
Unequivocally. That's really strong. Couldn't you just say, well, quantum particles are just weird? Or maybe there's some hidden mechanism we don't know about yet. Not jump straight to parallel universes.
Well, this is where he uses a kind of reality check, like Dr. Johnson kicking the stone. He says, if it can kick back, it exists.
Meaning,
if your explanation needs to invoke something, even something unseeable like a shadow photon, and invoking it lets you build a model that correctly predicts and explains the observable kickback, which in this case is the interference pattern, then that thing you invoked has to be real.
Because a non-existent thing can't cause a real effect.
Exactly. The sheer computational complexity needed to accurately model that interference pattern is essentially equivalent to tracking what happens to counterparts of that particle in other universes. That complexity, that predictive power, that's the kickback.
So if explaining the double slit pattern requires calculating what a shadow photon does in another universe, then that shadow photon and its universe must be real because they're affecting what we see here.
That's his argument. To deny their reality, while accepting the effect they explain, is basically sticking with an inadequate explanation, or maybe adopting a philosophical stance like instrumentalism, just focusing on prediction, not explanation.
He even says that other interpretations, like Bohmian mechanics, which seem like single universe theories.
Right. Even those, if you look closely, require tracking this incredibly complex pilot wave or something similar, which behaves computationally exactly as if it were coordinating vast numbers of these shadow particles across universes. So by this kickback or computational complexity standard, even Bohm's theory is effectively a multiverse theory in disguise.
Okay, but if the evidence is that fundamental, why is the multiverse idea still seen as, well, a bit out there? Why isn't it the standard view?
He gives a few reasons. Some scientists are genuinely just focused on prediction, shut up and calculate,
Yeah.
They're not losing sleep over the explanation. Others hold philosophical views, like positivism, that say science shouldn't talk about unobservable things. And let's be honest, the idea of infinite parallel universes is a lot to take in. It's counterintuitive, maybe even disturbing for some.
So some people just prefer not to go there.
Could be. But Deutsch's point is, if you really want to understand reality based on our best current physics, you have to grapple with the multiverse. He thinks it ultimately leads to a more rational, integrated picture.
Right. And what about the fact that we don't usually see this interference? Why is it so subtle?
Good point. It's not really that observation destroys interference, which is a common way people put it, but it's a bit misleading.
Okay.
Interference primarily happens between universes that are very, very similar, between counterparts of a particle that haven't gotten tangled up with different environments yet. As soon as a particle interacts with its surroundings in a way that leaves different traces in different universes, a process called decoherence, things diverge.
Right.
To then see the interference, you theoretically have to track and control all those affected environmental bits across all those diverging universes, which becomes practically impossible almost instantly. The interference is still there mathematically, but it's smeared out, hidden in the complexity.
Okay, that makes more sense than just saying looking at it changes it. So if that's the physics strand, let's shift to how we know things, epistemology. There's this classic problem, right? The problem of induction.
Yes, a huge philosophical puzzle. Basically, logic alone can't prove anything about the real world based just on observations. You could be dreaming, or a brain in a vat, or solipsism could be true, the idea that only your mind exists. Logically, those are consistent with any evidence you might get.
So if logic can't force us from observation to truth, how can observations ever possibly compel us to accept really radical ideas like curved space-time or parallel universes? How does science actually make progress?
This is where Karl Popper's ideas are so important for Deutsch. He argues scientific reasoning isn't induction. It's not about proving theories true from evidence, or generalizing like, I saw 100 white swans, therefore all swans are white. That's flawed logic anyway.
So what is it then?
It's about conjecture and refutation.
Yeah.
We guess explanations, bold conjectures to solve problems we have with our current understanding, and then we test them critically. We try to find flaws, try to refute them with experiments.
So evidence isn't used to confirm a theory, but to choose between competing explanations, to see which ones survive the attempts to knock them down.
Exactly. Science is a process of error correction. We keep the theories that best solve problems and withstand criticism. It's not about justifying belief through induction.
Okay, but then why are we justified in, say, building a bridge based on physics theories? If there's no logical guarantee they're true or will work tomorrow, we rely on them all the time.
That's a really crucial question. The justification doesn't come from some magical inductive principle like the future will resemble the past. It comes from the fact that our best current explanations, the ones that have solved problems and survived tests, already contain implications about the future.
The predictions are baked into the explanation itself.
Right. The theory that explains why the bridge stays up also predicts it will stay up under certain conditions. When we rely on the theory, we're relying on its entire explanatory structure, which includes those future-oriented assertions. Any new theory trying to replace it would have to explain everything the old one did and why the old one seemed to work. That severely constrains what it can say about the future, too. So our reliance is justified by the proven problem-solving power of the explanation, not some abstract guarantee.
Got it. That's a neat way around the induction problem. Okay, let's tackle another big one. Time. Everyone feels time passing, flowing. But Deutsch says that whole idea is basically nonsense.
Yeah, he argues it's fundamentally incoherent. He uses these thought experiments with diagrams. Like, if you imagine time as a line with moments like snapshots, and then you picture the present moving along that line.
Okay.
What is that present moment doing? Is its movement happening in another time that leads to an infinite regress? Or is the present just a single point that moves? How does a dimensionless point move across snapshots? The whole notion of flow gets tangled in paradoxes.
Our everyday intuition about time is flawed.
Deeply flawed, according to physics. Especially relativity. The picture physics gives us is more like the block universe or space-time.
Where past, present, future are all just there, like a four-dimensional block.
Exactly. Laid out. Nothing is moving through space-time itself. What we experience as change, or the flow of time, is just the difference between the contents of different slices or moments within that block.
To my feeling of now isn't some special spotlight moving along the block.
Nope. Think of it this way. Different snapshots of you exist at different points in the space-time block. Each of those snapshots experiences this moment as now, just like you experience your location as here. The you of 5 minutes ago isn't less real. It's just located at a different time coordinate. They aren't taking turns being the real present.
So the feeling of flow comes from memory, comparing the current moment to past ones.
Pretty much. It's the sequence of conscious states, each accessing memories of earlier states within the block.
Yeah.
That difference creates this subjective sense of passage.
Okay, wow. But if the block universe is static, how does cause and effect work? Doesn't A cause B? Doesn't that imply change?
Good question. In the block universe view, cause and effect isn't about one moment making the next moment happen because the moments are all fixed. It's about the laws of physics dictating the relationships between the patterns at different times.
So the laws determine the whole pattern across space-time.
Right. In classical physics, it was deterministic. The state at one time fixed the state at all other times. The laws link events in a necessary order. Causation is that lawful relationship, not one thing actively pushing another into existence. It's more like reading a story. The events are linked logically, but the pages aren't changing each other.
And quantum mechanics adds a twist.
It adds probabilities.
Okay,
The laws don't just dictate one pattern, but the probabilities for different patterns to exist across the multiverse. So the block isn't just one 4D structure. It's this vastly complex branching structure across many universes, with the laws governing the connections and probabilities within it.
Truly mind-bending stuff. Okay, from space-time to another key strand, computation and virtual reality. Deutsch brings back that Dr. Johnson criterion here, right, about the kickback.
He does, but applies it through computation. He defines complexity in terms of computation, how much processing is needed to simulate or describe something. And the idea is, if creating even the illusion of something requires a huge amount of computation, then that something must be physically real in some sense, because simulating nothing takes zero computation.
So back to quantum interference.
Exactly. Any theory that correctly predicts the interference pattern, even if it tries not to talk about other universes, must perform computations that are effectively equivalent to tracking those shadow photons. That irreducible computational effort is the kickback, signaling the reality of the underlying multiverse structure.
And he links this to how we even do science, to virtual reality.
Yeah, it's a really interesting idea. He suggests that scientific theories are basically like programs for generating virtual reality renderings in our minds. Our common sense view of the world, Earth is flat, only one universe. Those are just like early, low-res, inaccurate VR models.
And science is the process of debugging and upgrading those models.
Pretty much. We test our mental VR against reality experiments, find the bugs where the model fails, and refine the underlying code, the explanatory theory, to make a better, more accurate rendering.
Which leads to the Turing principle, the strong version.
Right. This is huge for Deutsch. He proposes it as a fundamental law of physics, on par with thermodynamics. It states that it's physically possible to build a universal virtual reality generator.
Meaning a machine that could simulate any physically possible environment.
Anything the laws of physics allow. And the really stunning implication he draws from this is, the laws of physics themselves must mandate their own comprehensibility.
Whoa, How does that follow? They require things like us to exist to understand them.
It's a chain of reasoning.
Yeah.
If a universal VR generator is physically possible, it could exist somewhere, sometime. And if it can simulate any physically possible environment, it must be able to simulate an environment governed by the actual laws of physics. Simulating those laws accurately, understanding them arbitrarily well, that requires physical systems capable of performing the necessary computations and holding that knowledge.
So the potential for understanding reality is built into the fabric of reality itself.
That's the idea. Reality contains the seeds of its own comprehension, physically embodied. He also talks about the virtual reality prison. It's hard to keep someone fooled by a limited VR forever if they keep probing and seeking explanations, because inconsistencies will eventually show up, forcing a revision of the model.
And he applies this computational thinking even to mathematics, to proofs.
Yeah, challenging the traditional view of proofs as purely abstract, logical things, separate from physics. He argues performing a proof is a physical process, a computation.
Like running a program on a physical computer, even if the computer is our brain.
Exactly. And he questions the classical idea that proofs must have a finite number of steps, pointing out that it depends on the underlying physics, thinks Zeno's paradox.
And quantum computation blows this up even more.
Absolutely. Quantum computers, by harnessing the multiverse, can theoretically perform computations that are impossible for any classical computer, no matter how large or fast.
Meaning they could find results, proofs even, that couldn't be written down as a classical sequence of logical steps, because the computation itself involves coordinating vast numbers of parallel computations across universes.
Precisely. The result might be verifiable, but the steps, in the classical sense, wouldn't exist. It shows how our intuition about computation, based on classical physics like Turing's original model, was incomplete because it ignored quantum reality.
Okay. So we have these four massive ideas: quantum physics multiverse, computation Turing principle, epistemology knowledge creation, and evolution. How does he actually weave them into one fabric? What's the connection?
He argues they're not just related, they're deeply interdependent. They share certain features. They were all resisted initially. They face similar kinds of criticisms like being naive or cold. But more fundamentally, they fill each other's explanatory gaps. For instance, how could evolution produce something as complex as life, or a brain capable of understanding the universe? That relies on the quantum stability of matter, which allows complex structures to exist, and on the computational possibilities allowed by the laws of physics, which the Turing principle addresses.
And how we gain knowledge, epistemology.
That whole process relies on the universe being comprehensible in the first place, which, again, ties back to the Turing principle mandating that physical possibility.
Yeah.
You can't separate them.
So it's not like physics is the base and everything else builds on top.
No, he sees it as non-hierarchical. Concepts from computation explain limits in physics. Ideas from epistemology explain how science progresses. Evolution explains the existence of knowledge creators. It's a web, a fabric. And knowledge itself becomes almost like a fundamental physical quantity, something that influences the universe.
Wow. And this unified view allows for some really out there theories, right? Like the omega point theory.
Yeah, that's an example he discusses, drawing on Frank Tipler's work. It's a cosmological theory about the far future, specifically in universes that might end in a big crunch.
I do.
The idea connects back to the Turing principle. A universal computer, to simulate everything possible, ideally needs infinite time and resources. Many simple collapse scenarios seem to cut off computation finitely.
Violating the full potential of the Turing principle.
Right. The omega point is a hypothetical state where conditions near the final singularity are just right to allow for an infinite amount of computation to occur. But getting the universe into that specific state might require active steering.
Steering? By whom?
By intelligent, knowledge-creating beings. The idea is that processing the information needed to guide the universe onto this computationally infinite path requires the continuous creation of new knowledge, right up to the very end.
So the theory implies that if the Turing principle holds and infinite computation is possible, then intelligence must survive and keep learning, essentially forever, to make it happen.
That's the gist of the inference. It suggests that beings like us, engaged in creating knowledge, might not just be a cosmic accident, but could play a necessary role in the universe's ultimate fate, driven by these fundamental principles of physics and computation.
That ties everything together: physics, computation, knowledge, evolution, all pointing towards this potential cosmic destiny. It's quite a picture.
It really is a remarkably integrated framework, trying to show how these seemingly separate fields are just different facets of one comprehensible reality.
So what does this all mean? We've taken a deep dive into a view of reality where the furthest reaches of physics, the nature of computation, the very process of gaining knowledge, and the mechanisms of evolution are not just related, but are fundamentally aspects of a single comprehensible fabric.
We've seen how quantum mechanics seems to imply parallel universes, how computation might link to the universe's ultimate fate, and even how our ability to understand it all might be required by the laws themselves.
It's a powerful, integrated picture. But here's where it gets really interesting. Thinking about that omega point idea and the role of knowledge.
Yeah.
Well, if the laws of physics truly mandate the existence of entities that understand them, as the Turing principle suggests, and if knowledge isn't just something in our heads, but a fundamental physical quantity, maybe even conserved across the multiverse, what does that tell us about our place and purpose?
That's the question, isn't it?
Is this human drive to understand, to create knowledge? Is it just some evolutionary quirk? Or could it be a genuinely necessary process, woven into the very structure of existence, maybe even essential for the universe's own future?
A profound thought to chew on.
Definitely something worth mulling over long after our deep dive concludes.